Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FETs, a physics perspective. This is lecture number 14 and the title of the lecture is high frequency modeling of MOSFET. So, the outline will be typically we will be looking at the concept of high frequency CV characteristics, which we have actually dealt in lesser details in our previous discussion. We will look at a general Y parameter model with an analog part of it, and then we look at the intrinsic transistor with time varying voltages. Then we will have a generalized Y parameter model for the MOSFET, and then finally end up looking at the unity gain frequency of the MOSFET. So, this is the overall outline of this lecture. Let us look at the high frequency CV characteristics. Now, we assume that when you do have a MOS capacitor, especially a MOS capacitor, and you are working at low frequencies, we assume that the carriers or the inverse charges which is acting as a carrier will be able to follow this applied AC signal, which we discussed in our previous discussion also. So, let us say you have let me say you have gates, right. I am only considering the intrinsic part, we are not looking at the extrinsic part at this stage, and we have an oxide layer metal and then followed by an MO and then I have a semiconductor. So, if you are varying this gate voltage in a fashion which is low frequency of the order of few hertz, then it typically means that your carriers are able to respond to the changes, and anything higher than that the inversion charge carriers will not be able to respond to that case, right. This is one thing. The second thing is that the frequency of the applied signal should be lower than that of the reciprocal or the minority carrier response time. What do I mean by that? I mean by that if you take tau as the minority carrier lifetime, right, a response time, then we basically say that before so let us assume that something like this, assume yourself to be a carrier and you respond to inputs from your friends and family, say within 1 minute, right. If you reduce that response to from 1 minute to 10 seconds, it effectively means that you will be able to accept larger responses within the same time frame. The same concept applies to a charge carrier in a MOS device, that if you are able to reduce the response time, then you will be able to increase the frequency at which the signals or the carriers will be able to respond to the input signal. Now, the minority carrier lifetime is generally estimated by the generation recombination current density, which is given by this formula which you see here, Jr equals to Q into Ni into Wd by tau, where Wd is the thickness, depletion width thickness. This is my depletion width thickness, depletion width. This is my intrinsic carrier concentration, and of course Q is the charge. So, lower the value of your minority current lifetime, larger will be the value of Jr. Jr is basically your generation recombination current density. Why? Because you see, very interestingly, so you have, let us suppose, holes and electrons available within that intrinsic MOS carrier, right. If you have electrons and holes available and you do not let them recombine, then obviously the charges will remain there, and by application of electric field the charges will move and a current will be formed. But if you are allowed to recombine, then the charges presence will be gone and you will not be able to record any current out of it. So, therefore, we come to one takeaway from this slide is that lower the value of the minority carrier lifetime response time, higher will be the frequency till which it can respond to the input signal. Now, if you look at the first point here, then we can say that the total depletion charge, right, is Q times Na acceptor and concentration multiplied width of the depletion, and if you divide Qd by Jr, I get this Na by Ni into tau. So, let us look this functionality Na by Ni into tau, right, tau will come in the numerator. This is a quantity which is Qd by Jr. Jr is the recombination rates which I told you previous slide, and QD is the depletion charge. Ni is almost constant, Ne is user dependent, and tau is again you can change it by the user. So, if your Na increases or accepted ion increases, this equation QD by Jr, that will go on increasing, which effectively means that you will have a larger ratio of the depletion charge available. Now, when you say the time taken to generate a minority carriers approximately equal to the depletion charge. So, if a depletion charge is larger, it will make it difficult for you to actually respond to the input signals, right. So, that is the reason. Let us come to point number 2, that any frequency higher than 100 hertz or approximately 80 hertz, around 80 to 100, actually till 150 depending upon the type of device you are taking, the inverter charge cannot respond to the applied AC signal. That is quite interesting, that such a low frequency somewhere between 80 to 150 is the reason why you have a very reduced response of a applied AC signal. Now, only the majority carriers can respond to the signal. Why? Because your minority current carriers are so small in number with a relatively high value of tau that it is not able to respond to any of the frequencies which you give, right. So, tau value is typically low in that case. When it is very low, then your Jr is very large, and therefore, a depletion charge of the majority carriers can respond to the signal. What is the depletion charge in an N-type enhancement mode MOSFET, if you look very carefully? So, in an N-type enhancement mode, there is an inversion charge which is electron, and the depletion charge is basically positively charged atoms, right. They are fixed in the nature, but they are not mobile, they are ions, and therefore, if you vary the gate voltage in a fashion, the depletion width will go on increasing and decreasing depending upon the type of gate voltage you are applying, depending on which the response time will change. Now, just to clarify your thought, that we generally write down that a high frequency capacitance, we have looked at in our previous discussion, it comes out to be 1 by C min equals to 1 by C aux plus 4 kT ln of Na by Ni by epsilon silicon q square by Na, right. T is the temperature, absolute temperature which we see. So, it is basically 4 kT natural log Na by Ni upon epsilon silicon q square into Na, right. This gives you a value of the minimum frequency which you could expect to see in this case. So, remember 1 by C min was how much? 1 by C min by my previous discussion, if you go back to my previous slides, 1 by C min was equals to 1 by C aux plus 1 by C depletion. This is basically 1 by C depletion which you see here, depending on the value of the acceptor ion concentration and the intrinsic charge carrier concentration. C aux, again, if I am assuming that my oxide thickness is very large, then my C aux will be relatively small, right, and then it comes into picture, right. If my C aux is relatively very thin, so if you remember C aux, it is nothing but epsilon aux by T aux. So, if your T aux is very small, your C aux is very large. So, C min will have that component more prevalent, which is minimum. So, the effective value on the RHS of this equation will be less than the least. Now, if you look at this expression C aux equals to epsilon aux by T aux, as the T aux value goes on reducing, which means that you have a thinner and thinner oxide layer available with you, then your C aux goes on increasing, right, oxide capacitance goes on increasing, which basically means that its contribution to the total value of C min actually starts to reduce. And therefore, you have to be very cautious that for very thick channel devices, when your T aux is very large, C aux is low. So, C aux low primarily means that they will contribute too much to the value of your C min. C min is basically the minimum amount of capacitance available to you at inversion, right. This is for the high frequency per unit area. Let us come to the CV characteristics. We have also again discussed this point. This is for an N channel enhancement mode, not a depletion mode, and therefore, you see the minimum value is shifted to the right of my VG depletion region, right. It is in the inversion region. So, I have an accumulation region. I have already discussed with you that C accumulation will be approximately equals to C aux, because there will be no depletion part here. As you further increase the value of VG, it starts to decrease for the reasons already discussed with you. Somewhere around inversion, onset of inversion goes to minimum, and then for low frequency goes to a higher value, and for high frequency it pumps down to the lower value. Now, typically if you plot a CV, so this is basically a CV characteristics. How we do it? By applying a slowly varying ramp voltage to the gate, right. So, I have a slow, so what I do, I have applied a DC bias slowly varying ramp, and superimposed on that you will have AC signals available with you. So, a small signal AC is superimposed over this ramp, increasing ramp or slowly varying ramp voltage. Now, that is the point, that if, however, if your ramp rate is very high, which means that you are ramping up at a very fast pace, right, then the ramping time is shorter, obviously, right, because this is more steeper. If you look at this expression, it effectively means that you are ramping up in a very fast pace. And if this ramping time is shorter than the minority carrier lifetime, then there will be obviously insufficient time for the inversion layer to form, and the MOS capacitor will be always going into deep depletion. That is what is written here. You see this part. What will happen, I am trying to tell you, is that if it goes beyond high frequency, what goes beyond high frequency? Not your AC signal, but also your ramping up signal, and you are ramping up very fast, right. When you are ramping up very fast, you give lesser amount of time to the minority carrier response time, and if it is shorter than the minority carrier response time, there will be insufficient time for the inversion layer to form, and therefore you will see that the MOS cap will dipping into deep depletion. Deep depletion primarily means that the overall cap per unit area will actually go down much more. So, if you just sort of recapitulate what we did in, at least for this part of the slide, is that so if I take an N, so this is for an N channel, let me write down, is an N channel enhancement mode device, and in this case what we are doing is that the N channel enhancement mode device, if you look very carefully, we have actually 4 regions of operation. The lowest one is the accumulation, where the total capacitance is C aux. Move forward till inversion, you get the minimum capacitance, that is C min, right, or the flat band capacitance, and then from there if you look at low frequency, it rises again because the carriers are able to respond to the value of the input frequency. If it is high frequency, it saturates, and if the frequency is further higher than high frequency, since you are not able to at all respond the time, there is no inversion layer formed, you go into deep depletion, and there is a decrease in the value of capacitance. So, ideally speaking, if you want the device to operate at deep depletion, your capacitance values will be very small, but understand at this stage that deep depletion will give you also a smaller amount of current. So, it is just not that your capacitance is low and you will get a better transient response, but since your currents are also smaller, you will get a latency time which is much larger, right, and that is the problem people face when they design CV characteristics. Now, so let me go to the next slide, please. So, the next slide is let me frame a question for you, and from here your understanding will be much higher, that when we do a high frequency measurement, right, is it possible to obtain a low frequency like CV? Low frequency CV is one which goes down, right, which goes down and becomes minimum and then again increases. When you are doing a high frequency, can we do that, right? If you form an N plus region adjacent to the MOS device and connect it electrical to the P type substrate, that is possible, right. Now, what will happen is this N plus region will be acting as a reservoir of electrons. So, there will be large electrons available, and they can actually supply large amount of minority carriers freely into the with the inversion layer. So, your basic, so the reason why at high frequency we were not able to emulate the curve going top, because we were not able to respond it. However, if we can insert artificially large number of electrons within the inversion layer during that process, obviously the device will respond to the varying value of the charge carriers, and again the voltage will again switch back to the higher value, right. So, therefore, look at the last statement of this slide, that in other words, the N plus region connected to the surface channel of the inverted layer will, this structure is similar to a gated diode, right. So, you will study about gated diodes. In gated diodes, it is normally on device. So, it is almost behaving like a depletion mode device rather than enhancement mode device. So, if you are supposed to convert a high frequency measurement to show a low frequency CV curve, good idea to have is a N plus region which is acting as a surface reservoir, insert large number of minority carriers. Once you do that, the device is able to respond to the varying values of the charge carriers. Let us come to the last part of this lecture. The last few slides will be there for this lecture, and we will do a Y parameter analysis. Now, Y parameter is sort of an admittance parameter, and we will see as we move along how what is the meaning of admittance, and we are again restricting ourselves to the intrinsic part of the transistor, and we are applying a time varying voltage at various points. Now, if you look at the left hand side figure as well as the right hand side figure, what we are doing is that my gate voltage, I have applied a gate voltage here. All small is basically a bias, and when we write ID or we say Vg, we mean to say it is a transient response which you see, a time varying transient response, and when we say ID, it is basically the DC current or voltage which you see. So, this parlance or this methodology will be used for the next few discussions. Now, if you look at this characteristics here, I have Vs, Vb and Vd. So, this is Vs source voltage, body voltage and the drain voltage, because of which there is a current which is flowing. There is a source current, there is a bulk current, there is a drain current and there is a gate current. So, there are 4 terminal currents, and there are 4 terminal voltages. And what we do now is, with this we apply a DC bias Vs, Vb and Vd to the applied small signal time varying signal. We applied a DC bias and see how does it work out in terms of discussion. So, most of the high frequency circuits are often use Y parameter, right. So, let us consider so how do you do it? Let us consider a transistor driven by a bias with a small signal voltage at each terminal. Now, we can write down the small signal voltages and currents can be represented by this value where Vg of t. So, the voltage at the gate, which is a time varying gate voltage, whose maximum value is mVg cos of omega t plus phi Vg. So, I have a phasor unit available to it, and the phasor representation is given as Vg equals to mVg e to the power j phi Vg, right. The standard. So, this is basically a cosinal signal. You can use a sinusoidal signal also, and what we do is that we superimpose this Vg of t with Vgs gate to source voltage or gate to source current will be formulated. Now, because of this there will be a current flowing through the device. Now, let me therefore explain to you how do we look at the current. So, a good way of looking at it is look at the last sentence and then we will go for the top one. So, between any two terminal, let us take K and L as two independent terminal of the MOS device. If a current IK flows through K terminal because of a voltage VL in the Lth terminal, then IK by VL is defined as my YKL. So, YKL, which is defined as admittance, is given by IK by VL, and we assume that all other nodes are having variation to be equals to 0, right. So, typically what we write down is, and let me show you if I have a graph for this. I do have a graph, yes, I can show you it from here. Look at this Y parameter associated with drain current. So, if I apply a drain voltage Vd and a current Id flows through it, then YDD is ID Vd. So, change in the drain current with respect to the change in the drain voltage. Similarly, if you change the gate voltage, then I get YDG, drain to gate will be ID, the drain current by the gate voltage. We have drain current with respect to source voltage gives you YDS, and YDB is ID by VB. So, you see all Y's are also small here, and the reason it is basically change in the current upon change in the voltage. It is not a DC bias which I am applying here, right, and that is the reason we define. And you see very interestingly, all the other value of voltages are equals to 0. So, you see Vg, Vb, Vs are equals to 0, Vd, Vb all equals to 0 in this case, right. Based on this we can actually calculate the value of the Y parameter. Now, if you go back to the slide which I was talking about, I can say that so I was assuming at this stage that all the other voltages are getting stopped. So, I can write down ID by applying the principle of superposition and saying that I will need to calculate the value of ID when you apply a VD and VG, VB, VS are all equals to 0. Similarly, try to find out ID when VD, VB, VS equals to 0 and there is only a VG applied. Similarly, try to find out ID when VD, VG, VS equals to 0 but VB is non-zero. Try to find out ID when VG, VD, VB is equals to 0 but VS is not equals to 0. And therefore, it consists of 4 terms 1, 2, 3 and 4. So, if you look down at this simplified expression, I get this to be ID equals to YDD VDD. What is YDD? We have just now seen what is YDD. YDD basically means this quantity del ID del VD. So, if I do this, then if I replace this ID by VD, so I get ID here, right. Similarly, IDG is drain to gate, get cancelled out, I get again current. YDB is drain current with respect to bulk voltage and drain current with respect to source voltage. When you add all these three together, I get the value of ID. And so, therefore, the principle of superposition is applicable in this case for extracting the value of the drain current, right. And similar equation from other currents, we can write down the generalized equation is YKL equals to IK by VL. Well, all the other terminal potentials are 0 and this is the value of your Y parameter. So, Y parameter if you look is basically its expression or dimension is 1 by ohm and it is referred to as a MHO, right, mho. Or we also write them the way Siemens. So, millisiemens or Siemens we write down. So, it is basically 1 by ohm. So, when I say Y, I mean to say it is conductance or admittance which we say here in this case. Therefore, let me write down for you the generalized expression for all the 4 currents in a sense. I get ID equals to YD VDD, IDG, this and this. So, if you let us look at the first expression, let us look at any expression, let us look at this expression, let us suppose IG is YGD, YGD is del, or let me write down VG VD into VD, ID IG VD. So, cancels out, you remain IG. Similar YGG will be IG VG into VG, VG again I will left with IG. So, this will be IG will get added up. So, IG component will always get added up. So, if you want to express it in a much more detailed manner, then the way we do it when we use an EDA tool to explain this, we use a matrix formation and this is basically your YDD, YGG, YBB and YSS, and obviously this will be YDG, this will be YDB, YDS, so this will be YGG, YGB, YGS and so on and so forth. The principal diagonal is the element where you will see that those elements where the current, so the drain current with respect to the drain voltage YDD or gate current with respect to gate voltage YGG. So, all the principal diagonal terms are basically those expressions of admittance which flows through the same current through the same terminal if you apply the voltage the same terminal. And that is the reason a generalized expression is shown at this particular point. I have already explained to you this expression here. So, let me show you the generalized Y parameter model if you use the source terminal as a reference now, which means with respect to source we will show you everything else. So, you see let us look at this particular point first, the right hand side. You look, this is YDG VGS, YDG is what? Del ID, or let me put ID VG into VG. So, basically VG, it is basically ID which you get here. So, this is basically the drain current, right, which is flowing between drain and source of the device and therefore, it is connected between these two terminals. Similarly, look at YDB VBS, this is the current contribution because of the bulk, right, the current contribution because of the bulk, and we have YDD which is basically the current del ID or ID by VD will be giving you the admittance parameter for between source and drain. So, these are all 3 in parallel. So, they are additive in nature. Now, if you go to the other part where you have this source and you have gate and you have bulk on this side, then between gate and source, because source is grounded, you get YGG as a admittance. So, admittance will all, so when you say admittance, they will be actually in parallel, right, and therefore, you see this is YGD VDS. What is YGD? YGD is IG VD into VD. So, this VD VD cancel. So, this is the gate current. Similarly, this is also the gate current. So, this is the total gate current which is flowing from gate towards the source or towards the channel. But please understand, the values will be so large, or the values will be so small, admittance values will be so small. Why? Because the oxide thickness is pretty large, right, and therefore, there will be no direct tunneling happening between the oxide layer. So, admittance values will be typically very small, and therefore, the current contribution will be very small in this case. Similarly, you will also have a bulk to or a body to a drain current, right, a body to a drain current passing through the depletion region of the drain side, and that is given by this quantity here. And then you will have a bulk to gate current which will be flowing because of VGS. So, these two are primarily, so if you compare this with your standard MOS model, then this quantity YBG VGS is basically the current which is flowing at this stage. These two currents are primarily at this and this, right. Let me name it as X and Y. So, this is X and Y, this is say A and B. So, this is B, and what is this YBD because of VDS, which is basically at this particular point, this one, let us suppose A, this is B, correct. So, there are 4 currents flowing, and because of that there are 4 admittance parameters available to me, and this basically is the current which is flowing here. Let me name it as say A prime B prime. So, A prime B prime will be available to you. So, there are 4 effective terminals available, and there are 4 currents flowing through the device, and that is the reason you see this effective values which you see here. So, a good way of writing this is, if you look at the right hand side, I have source, gate, drain and bulk. So, the Y parameter between drain and bulk is shown here, YDD, you have YGG and YSS, and these are the currents which are flowing from source to bulk, from gate to bulk and from drain to bulk, right, and these are the 4 parameters which gives you a effective value which you see here. So, with this, let me stop today's lecture, and when we meet next time we will start with the further high frequency modeling of the MOS transistor. Thank you.